Today we are looking at a tool called the comparison test, which lets us decide whether a series converges just by comparing it to another series we already understand. Here is the idea in plain words. Suppose the terms of one series are always squeezed between 0 and the terms of a second series. Then, if the larger series converges, the smaller series must also converge, and if the smaller series diverges, the larger series must also diverge. Let us prove this from first principles. Say we have two series, a smaller one and a larger one, and every term of the smaller series lies between 0 and the matching term of the larger series. Define the partial sum of the smaller series up to some number n as the sum of its first n terms. Define the partial sum of the larger series the same way, up to that same number n. Because each term of the smaller series is less than or equal to the matching term of the larger series, adding up term by term tells us the partial sum of the smaller series is always less than or equal to the partial sum of the larger series. Also, because every term of the smaller series is non-negative, each time we add one more term, the partial sum can only stay the same or grow, so the sequence of partial sums of the smaller series is increasing. Now suppose the larger series converges, its partial sums approach some fixed finite value, so they are bounded above. Since the smaller series partial sums are always less than or equal to the larger ones, the smaller series partial sums are bounded above too. Here is where the monotone convergence theorem does the work. It says any sequence that is increasing and bounded above must converge to some finite limit. Our smaller series partial sums are increasing and bounded above, so they converge. That means the smaller series converges. The same reasoning flipped around gives the other half. If the smaller series diverges, its partial sums grow without bound, and since the larger series partial sums are always at least as big, the larger series partial sums must also grow without bound, so the larger series diverges. Check this proof. We used only that terms are non-negative, that the inequality holds term by term, and that increasing bounded sequences converge. Every step used a fact we already trust. Now let us switch to a genuinely different proof. Instead of building up partial sums from scratch, this time we will use the Cauchy Criterion directly, which talks only about how much a series changes over any stretch of terms, never mentioning a limit by name. The Cauchy Criterion says a series converges exactly when its tail sums, meaning sums of terms from some point m up to some later point n, can be made as small as we like just by choosing m large enough. Suppose the larger series converges, then by the Cauchy Criterion, its tail sums from m to n can be made smaller than any target amount we choose once m is large enough. Because every term of the smaller series is non-negative and no bigger than the matching term of the larger series, the tail sum of the smaller series from m to n is trapped below the tail sum of the larger series over that same stretch. So the smaller series tail sums are squeezed below something that can be made arbitrarily small. That means the smaller series tail sums can also be made arbitrarily small, which is exactly the Cauchy criterion for the smaller series. So the smaller series converges too. Notice this root never spoke of a bounded increasing sequence or a supremum at all. It worked entirely with the size of tail sums shrinking, which is a genuinely different way of capturing convergence, not just the first proof said differently. Check this second proof. We never built partial sums upward, we only trapped tail sums between 0 and a shrinking quantity, and the Cauchy criterion finished the job on its own. Now here is a warning example showing why the terms must be non-negative. Take the smaller sequence to be an alternating sequence going 1, -1, 1, -1, and so on. Take the larger sequence to be the constant sequence, always equal to 1. Every term of the alternating sequence is indeed less than or equal to 1, so the inequality between the two sequences holds term by term, just as the test requires on the surface. But the constant series, summing 1 + 1 + 1 forever, clearly diverges, and the alternating series, summing 1 - 1 + 1 - 1 forever, does not converge either, since its partial sums just bounce between 0 and 1 and never settle down. Check this pathological case. The inequality held, yet it told us nothing useful, because the smaller sequence was not non-negative. This is exactly why the comparison test insists on terms squeezed between 0 and the larger series, not just any inequality between two series.